Good morning, students. Welcome to this session. In this session, we will look into the RC problems. In the previous section, we looked into RC, RL analysis and problems based on the RL circuit. That is the series combination of a resistor and a inductor. Just to recap the analysis of the series RC AC circuit. In case of a series RC AC circuit, we have a resistor connected in series with a capacitor having a inductive capacitance of Xc, that is Xc is equal to 1 by 2 pi Fc or is equal to 1 by omega C. This series combination is connected across a alternating voltage source represented by V is equal to Vm sin omega t, and the RMS value is represented by the capital V. This will result in a current in the circuit. This will result in the current in the circuit represented by the instantaneous value lowercase I or the RMS value capital I. Now, for the analysis purpose, whatever the voltage that is applied V across this series combination will get dropped across both the components. The voltage across resistor is VR, voltage across capacitance is VC. Now, the phasor sum of VR and VC will be equal to the applied voltage. Now, in order, before we proceeding it as a series combination, if we apply the analysis for the pure resistance, if we consider this as a pure resistance, and VR is the voltage that is applied across that, and I is the current that is flowing. If we draw the phasor diagram, we will have VR and I both are in phase. Now, if we consider this, the pure capacitance applied with the voltage VC and the current is I. If I draw the phasor diagram, in case of a pure capacitance, current leads the voltage by 90 degree. You can see the current, this is leading the voltage VC by 90 degree. And just if we merge these two, just you rotate this one so that this is I and this is VC, and we combine these two. This is how we get the combined phasor diagram. In the combined phasor diagram, you can see this is the voltage across the resistor and this is the current, both are in phase. This is the voltage across the capacitance and this is the current in the capacitor. The current is leading with respect to VC by 90 degree. Now, if we join these two, this is nothing but the applied voltage represented in the RMS value V. From this diagram, this angle is phi. The current, this is the resulting current and this is the applied voltage. Angle between them is phi. And if you see, this is a rectangle triangle. What we get is like we can write V is equal to square root of VR square plus VC square. So that is how we get this equation. V is equal to I into square root of R square plus XC square. V by I is always the opposition offered by the circuit. In this case, it is a RC circuit that is given by square root of R square plus XC square, which is nothing but the impedance of the circuit. Therefore, impedance Z of the circuit, Z is equal to square root of square root of R square plus XC square, where XC is equal to 1 by omega C is equal to 1 by 2 pi FC. And how to find the angle between the voltage and the current? Angle between the voltage and current is tan of this angle, tan phi is equal to minus VC by VR, or if I represent VC as IXC, VR as IAR, then tan phi is equal to minus XC by R. So the phi angle is what? Tan inverse of minus VC by VR or tan inverse of minus XC by R. Once we know this angle, then what is the equation for the applied voltage? The applied voltage equation is V is equal to Vm sin omega t, and the resulting current I is equal to Im sin omega t plus phi. So you have to remember that. So this is the current equation. And what is the power consumed in the RL circuit? That is given by P is equal to instantaneous power consumed is equal to the instantaneous voltage into instantaneous current, that is Vm sin omega t into Im sin omega t plus 5, or we can represent it as P is equal to power consumed in resistor plus power consumed in the capacitor. We know that power consumed in the resistor is I square R and power consumed in a pure capacitor is 0. Rewriting this, we get the equation, power equation as P is equal to VI cos phi. Now, if you remember this voltage impedance triangle, this side is VR, that is I into R, and this angle is phi. Okay, that is the phase angle, and this is minus VC, that is I into XC, and this is the applied voltage V into IZ. So if we just take out the I, what we get is this is a voltage triangle, and this is a impedance triangle, and this is phi. Using these two triangles, we can get all the equations what we derived. Only one thing you have to remember is the equation for voltage is V is equal to Vm sin omega t, and equation for the current is I is equal to Im sin omega t plus phi. And impedance Z is equal to, from this triangle we can find out, and tan phi again from this triangle or this triangle, and cos phi. What is the cos phi? Cos phi is called as the power factor of a circuit. The cosine of the angle between the voltage and the current, that is phi, is called as a power factor, which can be represented by R by Z or VR by capital V, and power is equal to P is equal to VI cos phi. Now we will solve some problems based on the series combination of the RC circuit. So these are the problems from Theresia book. You can refer to any other book. Theresia gives a good variety of the examples which will cover most of the scenario. That will be helpful for your examinations. Inductive word. Okay? So non-inductive means it is just the pure resistance, nothing else is there. Okay. So capacitance C 79.5 microfarad is connected in series with the 30 ohm resistor, and this series combination is connected across 100 volt comma 50 hertz supplies, and this 100 volt is nothing but the RMS value of the supply voltage, and this is the frequency of the supply voltage 50 hertz. What we have to find the impedance, current, then phase angle phi, equation for the instantaneous value of the current. So once we know the capacitance, and if frequency is given, the first thing you have to do is you calculate the XC. Similar to the RL circuit, what we did, whenever there is a L value of the inductance is given, value of the frequency is given, the first thing we do is we calculate the XL. XL is equal to omega L 2 pi FL. In case of a capacitive RC circuit, the capacitive reactance is XC is equal to 1 by omega C or 1 by 2 pi FC. F value is known, C value is known, and C should be represented in the farad, that is 79.5 into 10 raised to minus 6 farad. So that 10 raised to 6 is coming to the numerator as that, like in the denominator it is 10 raised to minus 6, numerator it is 10 raised to plus 6, divided by 2 pi 50 into 79.5, we get the XC as 40 ohms. Now, what is the first thing we have to find? Impedance. We already know the equation for the impedance. What is impedance? Z is equal to square root of R square plus XC square. R is given value, and even before this, you have to draw the circuit diagram. First thing, whenever you see a problem, is draw the circuit diagram and write down all the given values. Then by substituting R and XC value, square root of 30 square plus 40 square is equal to, yes, we get it as 50 ohm. The impedance of the circuit is 50 ohm. Then what is the circuit current that will flow in the circuit? It is given by the relation V is equal to I into Z. Okay, or I is equal to V divided by Z. V is known, that is V is given, that is 100 volt, and Z we calculated 100 by 50, 2 amperes. What is 2 amperes? 2 amperes is nothing but the RMS value of the resulting current in the circuit. Then next is phase angle. We have to find the angle between the voltage and the current. How to find that one? If you remember the impedance triangle, right? From this circuit. So from this is the phi. This is the phi. From this impedance circuit, we can easily write the tan phi. Okay, tan phi is equal to Xc upon R is equal to 40 upon 30. Xc is 40, we calculated. R is given 30. We get it as 1.33, and phi is equal to tan inverse of 1.33, that is 53-degree lead. Whenever we have the capacitive component, okay, along with the resistance, the current is always leading. So what is the meaning of 53-degree lead? In this particular RC circuit, the current is leading the applied voltage by an angle 53-degree. In case of a pure capacitance, current will lead the applied voltage by 90-degree. Here it is not leading by 90-degree because there is some resistance. It is leading by lesser than 90-degree, but it is leading the voltage by 53-degree. Now, fourth is equation for the instantaneous value of the current. So what is the generic equation for the instantaneous current? I is equal to Im sine omega t plus 5. You have to remember it is I is equal to Im sine omega t plus 5. And how to find out the Im? We know the RMS value of the current, that is I, and we know the relation between the RMS value and the max value or the peak value. We know that the RMS value of the current is equal to 0.707 times the peak value, or Im is equal to I divided by 0.707, that comes as 2.828 amperes, and omega is equal to 2 pi f. F is known, that is 50. We get it as 340. Now what is the equation for the instantaneous value of the current? I is equal to Im, that is 2.828 sine of omega t, that is 314t, plus phi. Phi is 53-degree. So this is nothing but represented in units amperes. Okay, next problem. A capacitor and a resistor are connected in series across 120 volt 50 hertz supply. The circuit draws a current of current of 1.144 amperes. So this current is nothing but the RMS value of the current, that is capital I is equal to 1.144 amperes. If power loss in the circuit is 130.8 watt, means total power consumed in the circuit, P is equal to capital P is equal to 130.8 watt. Find the value of resistance and capacitance. So here they have given the resulting current, they have given the applied voltage, they have given the frequency, and they have given the what is the power consumed that is in the circuit. Now we have to find what is the value of the resistance and what is the value of the capacitance. Now the power loss occurs in resistance only, as capacitor consumes no power. So if you remember this here in our analysis here, when we were calculating the power consumed in the capacitor, RC circuit, P is equal to power consumed in resistor plus power consumed in capacitor. So this power consumed is 0. P is equal to I square R. So we can use that relation, P is equal to I square R. P is given 130.8, I is given 1.144 amperes. Therefore, R is equal to P by I square, 130.8 divided by 1.144 whole square, that we get it as 100 ohm. So what is the resistance of the circuit? It is 100 ohm. Now we have to find capacitance. Even before we find the capacitance, we have to find the Xc. that is capacitive reactance. Once we find the capacitive reactance, Xc is equal to 1 upon 2 pi Fc. F is given, we can calculate the C, that is the capacitance. Now, we know R, then what is the equation? Z is equal to square root of R square plus X square. Xc we have to find, R is known, but Z is not known. So we can calculate the Z because the RMS of the value of the voltage is given, RMS value of the current is given. Therefore, the equation V is equal to I into Z. We can read Z is equal to V by I. Z is equal to V by I. V is 120. I is 1.144 amperes. We get the circuit impedance as 104.9 ohms. Now Z is known, R is known. We can rewrite the equation Z is equal to square root of R square plus Xc square as X is equal to square root of Z square minus R square. What is Z? 104.9 whole square minus R 100 square. That we get it as 31.7 ohm. So value of the capacitive reactance is 31.7. Now, therefore capacitance, we know that Xc is equal to 1 by 2 pi Fc. Rewriting that equation, C is equal to 1 by 2 pi Fxc. And all these values are known. F is known, Xc is known. If you substitute that one, you get it as 100 into 10 raised to minus 6 farad is the capacitance, or 100 microfarad is the capacitance. Okay, we have one more problem here. We have 100 ohm resistor and 400 microfarad capacitors. They are connected in series to an sinusoidal supply. The circuit current is 5 amperes. Calculate the supply frequency F and phase angle 5 between the current and the voltage. So this is the problem that is given. We have 10 ohm resistor is given. C is equal to 400 into 10 raised to minus 6 farad. First thing you calculate is Xc, and what else is given? It is connected to a sinusoidal voltage supply. Resulting current capital I is given 5 amperes. So these are the given values. Draw the circuit diagram and write all the given values. So we have R connected in series with the capacitance, and the current flowing is 5 amperes. So here you can see the current flowing is 5 amperes. We know that this V is given. Okay, maybe it is just here. It is connected in series to a 60 volt sinusoidal supply. Capital V is given. That is V is equal to 60 volts is given. Now we can find the VR. This voltage is will get dropped across the resistance and the capacitance, and VR is what? I into R. That is 5 into uh, 5 into 10, that is 50 volts. Once we know the VR value and V is known from this voltage triangle. If you remember, you have to just remember those triangles. Voltage triangle, basically it is nothing but a phasor diagram. If you remember the phasor diagram, then analysis is very easy. So here you can see VR and I are in phase, and current I is leading VC by an angle 90 degree, and this line is voltage, this angle is phi. So overall what? The resulting current I is leading the applied voltage by an angle phi. That's it. Now from this triangle, VR is known and V is known. We can calculate VC as VC is equal to square root of V square minus VR square. This is just applying the Pythagoras theorem. Is equal to square root of 60 square minus 50 square. We get it VC as 33.17. Once we know what is the uh, voltage across the capacitance, VC is equal to I into Xc. So biggest common mistake what I have seen by many students is VC is equal to, they will say I into C. So instead of Xc, it is not the C. And similarly, in case of inductors, VL is equal to I into L, which is wrong. It is VL is equal to I into XL. XL is the inductive capacity, inductive reactance, and XC, this is VC is equal to I into XC. XC is the capacitive reactance. That you have to be very, very careful. Therefore, XC is equal to VC divided by I. VC we just calculated that 33.17 divided by the resulting current is given 5 amperes. Therefore, XC is equal to 6.634 ohms. Now, first, what is the first thing we have to find here? We have to find the supply frequency and the phase angle. Now, we know what is the value of XC, right? Once XC is known and C is already given. C they have given as my 400 into 10 raised to minus 6 farad. Therefore, F is equal to 1 by 2 pi C into XC. Rewriting the equation, XC is equal to 1 by 2 pi FC. You are taking the F out and you are making it equal to 1 divided by 2 pi C into XC. C is 400 into 10 raised to minus 6. Then X is 6.634. We get the supply frequency as 60 hertz. Now the phase angle, you can use tan phi is equal to VC by VR, and VC is 33.17 and VR is 50. We get it as 0.6634. Therefore, phi is equal to tan inverse of 0.6634, that is tan inverse, and we get it as 33.6 degree leading. So in this particular circuit, the current will lead the voltage by an angle 33.6 degrees. So that is the phase angle. Next, calculate capacitance of a condenser to be connected in series with 100 volt 80 watt lamp to enable it to be used on a 200 volt 50 hertz supply. So what we have to calculate? Capacitance of a condenser. So condenser capacitance, you can capacitor, you can take it as a synonym. So we have to find the capacitance which is connected in series with a 100 volt 80 watt lamp. So lamp, what you can take is as a pure resistance circuit. So using these two parameters, you can calculate the resistance, and they are connected across 200 volt 50 hertz supply. So first thing, now draw the circuit diagram. We have this is a 100 volt, the voltage across this is 100 volt, and 80 watt, that is the power consumption. C is the capacitance unknown that we have to find out. Vc is the voltage across the capacitance. Capital V is given 200 volt and F is 50 hertz. Now, the current that is flowing in this particular uh, lamp then can be calculated as power consumed here is P is equal to V into I, right? P is 80 and V is 100. Therefore, I is equal to 80 by 100, 0.8 amperes. So how much current is flowing in the circuit? 0.8 amperes. And how did we find out that? We know what is the power consumed in the resistor. So this you can just assume as a one resistor, right? Capital R. This is a one resistor. What is the power consumed in the this resistor in terms of voltage and current? P is equal to V into I, and we are interested in I. I is equal to P divided by V. P is 80 divided by V is 100. We get it as 0.8 amperes. This is the phasor diagram. This is 100 volt. This is the current. How much is the current? 0.8 amperes. And this is the VC, not yet known. This is the applied voltage 200 volt. Now we know V and we know VR. We can calculate VC. What is VC? VC is equal to square root of V square minus VR square, that is 200 square minus 100 square. We get it as 173.2 volts. Once we know VC and we already know what is the current, VC is equal to I into XC, or XC is equal to VC divided by I, that is 173.2 divided by 0.8 amperes. We get it as 216.5 ohms. And finally what you have to calculate, capacitance. Xc is equal to 1 by 2 pi fc. C is equal to 1 divided by 2 pi f into xc. F is given, xc you calculated, so you get it as 14.7 into 10 raised to minus 6 farad, or 14.7 microfarad. Two elements in the circuit consume 700 watt and has power factor of 0.707. So here what it says is like power consumption is 700 watt and power factor is 0.707 leading. Meaning of that is it is nothing but a RC circuit. If the applied voltage is, it is given in this form, 141.1 sine of 314t plus 30. So this is the phase of the voltage. Even the voltage itself is starting by an at an angle 30 degree, and from that 30 degree current will lead. Okay, we have to take it like that. Okay, so you can leave that problem. So that is about this kind of a problem. So whatever the problems we just now discussed, those problems are more than sufficient, and you will be asked similar kind of problems in the exam. And if you are able to do that kind of problems, if you are able to solve, then it is sufficient. Like you should be able to solve any kind of a problem in the final exam. Now we come to the last combination, that is the series combination of a resistor, inductor, and capacitor. So all the three will be connected like this. So you can see a pure resistor, pure inductor, and pure capacitor are connected in series, and this series combination is connected across a voltage source, and this voltage source is given by V is equal to Vm sin omega t, and this voltage that is applied to the series combination of RLC, it will result in a current which is represented by the RMS value of capital I, and we will see what would be the instantaneous equation for this current. And the applied voltage V will get dropped across each of these components. The voltage across the resistor is capital VR, voltage across the inductor is capital VL, voltage across the capacitor is capital VC. These are the voltages. Now, the applied voltage would be the phasor sum of VR, VL, and VC. Now, if we draw individually, you can just imagine how it would be. This is the current. That current will flow through each of this component. In case of a VR, we will have the current and VR both in the same line. So in case of a pure resistor, the angle between the voltage and the current is 0, or we can say the in case of a pure resistor, current and voltage are in phase. So that is the first one. The second one, in case of a inductor, the applied voltage across the inductor is VL, the current resulting current is I. And what would be the relation here? The current I would lag the voltage VL by 90 degree in case of a pure inductor. So that we have to draw as a diagram. So if this is VL, okay, on the x-axis is VL, then on the minus y-axis we have the I. Therefore, the current lags the voltage by 90 degree. In case of a pure capacitance, if we find the relation, the voltage that is across the capacitance is VC, the current that is flowing is capital I, and what is the relation between the current that is flowing and the applied voltage V? Current leads the applied voltage VC by 90 degree. If we draw it, if VC is on the x-axis, then I would be on the positive y-axis, leading the voltage by an angle 90 degree. If we combine all those things, right? So if I take a common reference of this I, okay, now you can see this is the O and A is nothing but the VR, that is the voltage across resistor, and O and A, O and I. So, okay, this is the current. This is the current that is flowing in the circuit. So, if you see VR and I, they are in phase, or the angle between them is 0 degree. Both are on the same line. Now, how do you write the VL? We know that in case of a uh, pure inductor, the current would lag the voltage by 90 degree. Now, you will from point A, you will draw VL like this. Okay, AB represents the VL. And what is the VL? VL is the voltage across the inductor. And if you see here, again relation, AB is nothing but VL, and this is the current. Current is lagging the voltage VL by an angle 90 degree, isn't it? Right? So this is AB is VL, and this is the current. Current is lagging the voltage by an angle 90 degree. So that is the representation of VL and I. Now last is VC. Now we know that in case of a capacitance, current will lead the VC by 90 degree. That's why AC, okay, AC is representative of the voltage across the capacitance, that is VC. Now if you see the current, current is leading, so this angle is leading the voltage by an angle 90 degree. So this is the complete phasor diagram. So we have, this is OA, that is representative of VR, voltage across resistor. AB, that is the voltage across the inductor, that is VL. And we have AC, which is the voltage across the capacitance, which is VC, and this is the current. So current is in phase with VR, current is lagging by 90 degree with respect to VL, current is leading VC by an angle 90 degree. Now you can see the AB, that is VL and VC, they are on the same exact axis, right? Y axis. So they can be algebraically, they can be combined. So what would be the combined value? This is the positive value VL, and this is negative value VL minus VC. Let us, for just for the argument, we assume that VC is less than the VL. So let us just assume VL is 100 and VC is 50. What would be the effective voltage? VL minus VC, that is 100 minus 50, 50. So it would come somewhere here on the positive line. Now, this point D. This point D is what? AD is representative of a VL minus VC. O is VR. And phasor sum of VR and VL minus VC is nothing but the applied voltage V. And the angle between OD, that is applied voltage, and this current. Okay, so you can see clearly the current is lagging the applied voltage by an angle phi. Okay, this is how the analysis, and we can apply the Pythagoras theorem to OAD, this triangle. We get it as V is equal to square root of, one side is VR square, plus another side AD is VL minus VC square. And we know that what is the VR in terms of the the resistance. VR is equal to I into R, that is I into R. And we know that VL is I into XL, I into XL, and VC is I, the current I that is flowing into XC, I into XC. So from this equation, I get the I square common. So square root of I square is I, it will come out of the square root. So V is equal to I into square root of R square plus XL minus XC square. Therefore, I get V by I. Suppose if you take, this is V divided by I. V by I is equal to what? Square root of R square plus XL minus XC square, which is nothing but the opposition offered by the circuit to the flow of the current, which is nothing but the impedance. So thus, what is impedance is equal to? Z is equal to square root of R square plus XL minus XC square. and the power factor cos phi is equal to r by z. So from this triangle, cos phi is equal to what? This is r by z. If you convert this as a triangle, this impedance triangle, this is r, this is xl minus xc, and this is z. So it is cos phi is r by z, and z we know that square root of r square plus xl minus xc square. Similarly, tan phi is equal to what? From this triangle, tan phi, it is opposition. Okay, opposite side is VL minus VC divided by VR. Okay, VL minus VC divided by VR, or this is XL minus XC divided by R. So if you remember one voltage triangle, how to get the one voltage triangle for RL, same thing for RC, same thing for RLC. In case of a RLC, only one difference here is we have VL minus VC, because both are in the same axis. We have VL minus VC on one side. Now, the interesting scenario here is, depending upon the value of XL and XC, there are a couple of scenarios we get. Since XL, XC, and R are known, the phase angle phi of the circuit can be determined, and power consumed, we get it as same. So power consumed is equal to power consumed in the resistor plus power consumed in the capacitor plus power consumed in the inductor. Power consumed in the pure inductor and pure capacitor is 0. So therefore power consumed in the circuit is I square R, which we can write it as a generic equation of a power consumed in any AC circuit, that is V into I into cos phi. Therefore power is equal to RMS value of the voltage into RMS value of the current into cos of the angle between the voltage and the current. Now, there are three different scenarios I told you, because of the based on the how the value of the XL and XC. Okay, so we can have three possibilities regarding XL and XC value. Either I can have a XC value larger than the XC value, that is one. Second one is XL value is equal to XC value, that is second scenario. The third scenario is XL value is less than the XC. So three possibilities are there. And what is the first possibility? When XL minus XC is positive, meaning is what? XL is greater than XC, means the circuit is more inductive. Okay, even though there is a capacitance is present, but it is more inductive. For example, XL is 100 ohm and XC is 50 ohm. This XL minus XC is 100 minus 50. So 50 ohm, that is 50 ohm is a inductive reactance. So it is more inductive. The phase angle phi is positive and circuit will be inductive. So in other words, such a case, the current I will lag behind the applied voltage V by an angle phi, the value of phi being given by the equation 2 above. So already we calculated the phi. Now, simple way to remember, if XL minus XC is positive, that is XL is equal to greater than XC, means what? The circuit will be more inductive. It will behave more inductive. Or you can think of this circuit, instead of RLC, it is a RL circuit. And in case of a RL circuit, what is the relation between voltage and the current? The current lags the voltage by an angle phi. Okay, and how to find the phi? This is the equation. Tan phi is equal to VL minus VC divided by VR, or XL minus XC divided by R. That is the first scenario. And second scenario is what? XL minus XC is negative. What is the XL minus XC negative? Means XC is greater than XL, or you can say XL is lesser than XC. The circuit will be more capacitive, right? Because XC is more, the circuit will behave more capacitive, or you can think the circuit as a RC circuit. And what happens in the RC circuit? The current will lead the voltage by an angle phi. Okay, so XC greater than XL, phase angle phi is negative, and the circuit is capacitive. That is to say, the circuit current I leads the applied voltage V by an angle phi, and the value of the phi is given by the same equation. So simple way, Xc greater than XL, meaning what? The inductive capacitance is more than the capacitive reactance is more than the inductive reactance. So circuit will behave more capacitive, or it behaves like a RC circuit. And in case of a RC circuit, current leads the voltage by 90 degree, and that phi angle can be calculated using this formula. Then accordingly, the third one is when XL minus XC is 0. What is the meaning of that? XL and XC are exactly equal. If XL is 50 degree, XC is 50 degree. So XL minus 60, 50 minus 50 is 0. So what is the meaning of that? There is no inductance or no capacitance. It is a pure resistive circuit. And what happens in a pure resistive circuit? It will behave, the voltage and the current will be in phase, or the phi will be 0. Okay, so from circuit diagram, uh, okay, so this is assumed VL is greater than VC. That's why you are seeing the current is lagging the voltage by an angle phi, and phi can be calculated using the formula given below, that is VL minus VC. Tan phi is equal to VL minus VC divided by R, or XL minus XC divided by XR. Now, just imagine VC is larger than VL. So, what would happen on the negative side? We have a VC value is more. So, the VL minus VC would be negative value. So, this capital, this V will come, this point will come somewhere here. So, applied voltage would be like this V. Now, you can see this is the applied voltage and this is the current. Now current is leading the voltage by an angle phi, and phi can be calculated with the same formula. The third scenario, this ABVL and this AC are exactly equal. So this point, each VL minus VC will come to 0. Then you can see VR is in phase with the current I. So that is how we analyze the RLC circuit. And how do we give the equation? Equation is very, very important. V is equal to Vm sin omega t. If this is the applied voltage, then the resulting current I is equal to Im sin omega t plus or minus phi, where Im is equal to Vm by Z. So Vm is the peak value of the applied voltage, and Z is the impedance of the circuit. What is the impedance of the circuit? Z is equal to square root of R square plus X minus Xc square. Now, for the current, we have omega t plus or minus phi. So, plus means what? It is current is leading the voltage, that is when the Xc is greater than XL. Or I can get I is equal to Im sin omega t minus phi, when I will get XL is greater than Xc, or the circuit will behave like a RL circuit. So that is when I get. And another scenario where phi is equal to 0, right? Phi is equal to 0 means what? VL is equal to VC, or XL is equal to XC, where VL minus VC becomes 0. Then I is equal to Im sin omega t. That time both voltage and current are in phase. So this is the impedance triangle. So voltage triangle, you just remember this. I did not. It is not given separately. Voltage triangle. This side VR, this side VL minus VC, and this is the applied voltage. So hypotenuse would be the applied voltage, and this is the angle phi. Okay. From this you can write the equation. So you can apply the Pythagoras theorem, and you can find what is tan phi. All those things can be done. Similarly, if we represent these values, this as VR is equal to I into R, V is equal to I into Z, VL minus VC is equal to I into XL minus XC. If we take off the I, what remains? R will remain here, impedance Z, this side XL minus XC. That is what is drawn here. This is XL minus XC, this is impedance, this is R, and this is the angle phi. Using this triangle, you can write the equations. And class, we will see the problem based on the RLC.